Greetings. This is the first lecture on the Riesz representation theorem. This is a result which holds in all locally compact Hausdorff spaces. On this lecture, we will mostly focus on introducing these spaces and discussing some of their useful properties. Before launching into these technical details, let's have a quick look at our eventual goal, the Riesz representation theorem. Consider a measurable space X f mu. For every function f in L1 of mu, define the complex number lambda mu of f by integrating f over x d mu. Then lambda mu defines a linear complex-valued map on L1 of mu. Such maps are often called linear functionals, and their theory is the main topic on the course Functional Analysis. Our functional lambda of mu has an additional special property, which is certainly not true of all functionals. It is positive. In this context, positivity means that if f is a non-negative function, then also lambda mu of f is a non-negative real number. This property is trivial. The integral of a non-negative function is a non-negative number. The Riesz representation theorem is a remarkable converse to this trivial observation. If lambda is any positive linear functional defined on a suitable space of test functions, then lambda looks like one of the functionals we discussed above. In other words, we can find a measure mu in such a way that lambda has the form lambda of mu for this measure mu. In yet another words, the abstract functional lambda is given by integration against the measure mu. This integration formula is valid for all the test functions on which lambda was initially defined. We will discuss these functions more precisely a bit later. Now that we know where we are headed, we start discussing the preliminaries of the Riesz representation theorem. This theorem will only work in topological spaces. In fact, already the definition of the test function space will require a topology, so the whole statement will not make any sense without a topology. Unfortunately, in addition, the theorem doesn't work in all topological spaces. We have to make two extra assumptions. The first, and perhaps the most restrictive assumption, is the following. We say that the topological space x tau is locally compact if for all points x in X, there exists an open set U containing X whose closure is compact. Of course, the Euclidean space Rd is locally compact because the closure of every ball is compact. On the other hand, there are plenty of examples of topological even metric spaces which are not locally compact. For example, any infinite-dimensional Hilbert space such as L2 or little L2 can never be locally compact. This will quite likely be an exercise. The Riesz representation theorem would work in all locally compact metric spaces. However, the statement of the theorem has nothing to do with the metric, so it will be more natural and elegant to state the theorem in topological spaces. Unfortunately, there is a little drawback. We need to make one extra assumption which would automatically be satisfied in metric spaces but may fail in some topological spaces. This is definition 2.4. We say that the topological space x tau is a Hausdorff space if two distinct points have disjoint neighborhoods. In other words, if x and y are distinct points in X, then there exist open sets U and V such that U contains X, V contains Y, and U and V are disjoint. As we mentioned, metric spaces always satisfy this property. If X and Y are distinct points, good candidates for the disjoint neighborhoods are the open balls Bxr and Byr, where r is the distance of X and Y divided by 2. Now it would be a good exercise to find a topological space which does not satisfy the Hausdorff condition. In the future, a topological locally compact Hausdorff space will be abbreviated to an LCH space. The Riesz representation theorem will work in every LCH space. The next task will be to prove a few lemmas in LCH spaces, and some of them would be substantially easier in metric spaces. Before we start this work, let's ask ourselves, is it worth the effort? Could it be that every LCH space is actually metrizable? And this would save us a lot of trouble. However, the answer is negative. Example 2.5 contains a simple, compact Hausdorff space which is not metrizable. And this space is an uncountable product of closed unit intervals, equipped with the product topology. I'm not sure if you are familiar with the definition of the general product topology, so I won't go further into the details. If you are familiar with this much topology, it would be a good exercise to think why this topological space is not metrizable. Now you will have to decide yourself if you ever plan to do analysis on this space. I would dare say that the Riesz representation theorem is most often really applied in metric spaces. Nevertheless, it's a good general principle to prove important theorems under the minimal assumptions. This way it's easier to keep track of what is really essential. We then start proving some preliminary lemmas. In the first one, lemma 2.6, we only need to assume that our topological space x tau is a Hausdorff space. So the local compactness assumption is not yet needed. Let K be a compact subset of X, and let X be a point from the complement of K. Then K and X have disjoint open neighborhoods. In other words, there are open sets U and V where U contains X, V contains K, and U and V are disjoint. Of course, if K is a single point, this statement is nothing but the definition of a Hausdorff space. We then begin the proof. As we just mentioned, the result is clear by definition if K is a singleton. Let's then consider the more general case. For every point y in K, choose two open sets uy and vy such that x is contained in uy, y is contained in vy, and uy and vy are disjoint. It may look confusing that x lies in uy, but recall that x is the fixed point which lies outside K, from the statement of the theorem. Now the sets Vy form an open cover of the compact set K. Since K is compact, we may choose a finite subcover, let's say V1, V2 through to Vn. This subcover is illustrated in the picture. All of these sets Vj have the form Vyj for some point yj in K, and we write Uj for the corresponding set Uyj, which contains X. Then we let U be the intersection of the sets Uj, and we let V be the union of the sets Vj. These sets U and V are shown in the picture as the sets bounded by the dotted yellow lines. It is clear that U and V are open disjoint sets. U contains X and V contains K. This is what we wanted, so the proof is complete. The next lemma, lemma 2.7, is a standard result from topology. Let x tau be a topological space, and let F be a family of compact sets such that the intersection of all of them is empty. Then there exists a finite subfamily F0 of F, such that already the intersection of the sets K in F0 is empty. This result is quite likely familiar to you from topology. If not, it's a good exercise in using the definition of compactness. Next, we get to the first key lemma about locally compact Hausdorff spaces, lemma 2.8. Let x tau be a locally compact Hausdorff space. Then the lemma says that if K is a compact subset of X contained in some open set U, then we can always squeeze an open set V between K and U, whose closure is compact and also contained in U. The claim of the lemma is illustrated in this picture. The proof is not difficult, and it's really easy if U is the whole space. Let's start with this case. By the local compactness assumption, every point x in K has an open neighborhood U of x such that the closure of U of x is compact. Now, by the compactness of K, some finite family U1, U2 through to U of n already covers K. Now we can define G equal to the union of the sets Ui. This is an open set which contains K, has compact closure, and whose closure is of course contained in the ambient space X. So if U is equal to X in the statement of the lemma, we can simply set V equal to G and the proof is complete. If U happens to be a strict subset of X, a little more trickery is needed, since the closure of G might meet the complement of U, which we denote here by C. Note that C is a closed set which is disjoint from K. The situation is illustrated in the picture here. As you can see, the yellow set G may intersect the complement of U. To fix this issue, we need to make G a little smaller. To do this, fix any point x from C and start by using lemma 2.6 to find an open set Wx which contains K but whose closure does not contain X. The existence of W of X was just based on the Hausdorff property, and we are not even claiming that the closure of Wx would be compact. One of the sets Wx is also shown in the picture. The closure of Vx does not contain X, but it may intersect the set C somewhere else. Here comes the main trick of the proof. We look at the family F of compact sets which are obtained by intersecting the closure of G, which was compact, and then the closed set C, and finally the closure of Vx. The indices of this family are the points x in C. All of these sets are compact and they are evidently contained in C. On the other hand, no point in C can be contained in all of them. Namely, if x is in C, then x is not contained in the closure of the set W of x. Therefore, the intersection of the whole family is empty. Now, by the previous lemma, lemma 2.8, already some finite subfamily of F has empty intersection. Of course, this subfamily can be written in the form closure of G intersected with C intersected with the closure of Wxi where I runs from 1 to n, and the points xi are chosen from C. The key property of this family is that its intersection is empty, as we have written here in equation star. Notice that C is part of this intersection. So one way to interpret this equation star is to say that the intersection of the sets closure of G intersected with the closure of Wxi is contained in U. Now we are nearly done. We define V to be the intersection of G with the sets Wxi. Then V is open and has compact closure since this closure is contained in the closure of G. The set V also contains K because G contained K, and also each of the sets Wxi contained K. Moreover, the closure of V is contained in the intersection of the closure of G with the closures of the sets Wxi. As we already pointed out, it follows from the equation star that this intersection is contained in U. Therefore, V has all the properties we desired and the proof is complete. The main purpose of the previous lemma is to prove the following result, which has plenty of independent interest even beyond the Riesz representation theorem. This result is proposition 2.9, which is commonly known as Urysohn's lemma. As before, x tau is a locally compact Hausdorff space. K is a compact set, and U is an open set containing K. In the previous lemma, under the same assumptions, we squeezed another set between K and U. And this time we squeeze a function. This function is called f. It is a continuous function with compact support, and this support is contained in U. Moreover, the function only takes values between 0 and 1, and it takes the value 1 at every point of k. If you think about this statement for a moment, and you also recall the previous lemma, the characteristic function of the set V constructed there would work as the function f, except for the problem that it's not continuous. So the idea is to somehow modify the characteristic function of V into a continuous function. This is not exactly as the proof goes, but it's a good heuristic. Before starting the proof, let's go over some light preliminaries. First, the notation CC of U stands for all the complex valued functions defined in U, which are continuous, and whose supports are compact sets contained in U. We might as well have asked that the functions f here are defined on the whole space X, because every function in CC of U can be extended to a continuous function on X, simply by setting the values to be 0 outside U. Next, let us just repeat what we already mentioned before. The main point about Urysohn's lemma is the continuity of f. Without this requirement, we could simply set f to equal the characteristic function of V, where V is the set constructed in the previous lemma. In the process of constructing the continuous function f, we will construct some auxiliary functions which are upper and lower semi-continuous. So let's recall what these functions are in definition 2.10. Let x tau be a topological space, and let f be a real-valued function on x, or possibly a function which is also allowed to take the values plus or minus infinity. This function is called lower semicontinuous, abbreviated LSC, if the superlevel sets of f are open. In other words, for every real number alpha, the set of points x where f of x strictly exceeds alpha is an open set. In a similar spirit, the function f is called upper semicontinuous, abbreviated USC, if the sublevel sets of f are open. In other words, the set of points where f stays strictly below a given threshold alpha is an open set. I have always struggled to remember which of these conditions means lower semicontinuity and which of them means upper semicontinuity. The idea of lower semicontinuity is, as far as I understand, that if f of x is strictly larger than a lower bound alpha, then you can shift x around a bit and you are still lower bounded by alpha. Upper semicontinuity implies a similar statement about upper bounds. Here are a few basic facts about upper and lower semicontinuous functions, which you can verify yourself as exercises. First, a real-valued function on x is continuous if and only if it is simultaneously upper and lower semicontinuous. Second, the characteristic functions of open sets are lower semicontinuous, and the characteristic functions of closed sets are upper semicontinuous. Third and finally, the supremum of lower semicontinuous functions is again lower semicontinuous, and the infimum of upper semicontinuous functions is again upper semicontinuous. Now we are fully prepared to prove Urysohn's lemma, but we postpone the argument to the next lecture. This completes the first preliminary lecture on the